Okay, you guys, before we get started, I think some advice I would probably give you is, as we work our way through this problem, is to realize you're gonna have to stop every little while and try to catch up and figure out where you are. This is not a very, very simple problem. So, but let's see if we can't do it. And what we're gonna try to do is we're gonna try to take the implicit, use implicit differentiation to take the derivative of this equation here, and it's 3 times the quantity x squared plus y squared. Quantity squared is equal to 100xy. And I'm going to start off with the idea that I'm going to take the derivative of both sides of the function. And if you don't mind, I'm going to do the left side first. So here's where I am right now. I'm focusing here right now, focusing on this side of the function. So I'm going to take this derivative here. As you can see, the derivative is a little bit tricky because we're going to have to use the chain rule here. So first thing I'm going to do is take the derivative of the outside part of the function. That is, pretending this part of the function is just a single variable. Just for a second, I'm going to take the derivative of the outside. So we get 3 times 2 is 6 right here. We're going to decrement this exponent by 1. So 2 minus 1 is 1. So it's to the first power. Then if you remember in the chain rule, what we have is f prime of g of x, that is to say the derivative of the outside, times g prime at x. That's the derivative of the inside. Well, the derivative of the inside is this portion right here, and the first derivative of x squared is 2x, and the first derivative of y squared is 2y dy dx. Now I'm going to just hold on to that just for a second, if you don't mind, and I'm going to take a look at this. And what I'm going to do here is I'm going to start looking at taking the derivative of this side, and I'm going to take the derivative here. I'm going to call this I'm going to use the product rule here. I'm just going to take the derivative here and let this be the constant multiplier. So we have, here's our f of x function, here's our g of x function. So I'll start to make my list. F of x is equal to x, f prime at x is equal to 1. This is our g prime at x for this, and g prime is equal to y. And then we need g prime at x, and we know that the first derivative of y is dy dx. It's going to take that, remembering that we're using the product rule, and the product rule is f of x times g prime at x plus g of x times g of x times f prime at x. I'm going to go ahead and do that, put my pieces in place. F of x was x, g prime at x, if you look over here, was dy dx. G of x was y, f prime is 1. I guess I should have written a 1 here to show that I multiply, but take my word for it that y times 1 is y. So we have all that together. Now we're going to go ahead and distribute this 100. So 100 times x dy dx is 100x dy dx, and 100 times y is, of course, 100y. And that gives us this mess down here, doesn't it? Now just a little bit of algebra here, because this doesn't look a lot like up here. So if you're wondering where this came from, I decided to just simplify a little bit. So I took the 6 here, and I multiplied it by this piece over here. So of course 6 times 2x is 12x. 6 times 2y dy dx is 12y dy dx, and this x squared y squared is here. Okay? All right. And we still have this piece here. Now, if you can remember FOIL, how FOIL works, of course, we have 2 binomials here, and here. And we do this expansion, we'll do this 12x times x squared, and then we'll do 12x times y squared, won't we? Well, that's this. This 12x is this 12x. This x squared plus y squared is this one. All I did was just break it into groups. And then I'm going to take this 12y dy dx, and I'm going to multiply it here. I broke up the 12y and the dy dx for convenience sake, and I think you'll see why in a second. And then I can multiply this times this, and that's me doing this times this, right? Okay, so it's a little bit tricky. If you look here, now what I'm starting to notice, and I put it in orange so hopefully you'll notice it too, is I have dy dx here, and I also have dy dx here. And we're solving for this derivative, so what we want is to solve for dy dx. So what I'm going to do is just a little bit of algebra, move stuff around. So what I'm going to do is, what I've done here is I'm going to move everything that has dy dx to this side, and everything that doesn't, I'm going to move to this side. So I'm going to subtract this 12x times x squared plus y squared, and that ends up right here. You can see that I subtracted it here. Subtracted it from both sides, yeah? A little bit of algebra. And then I subtracted 100x dy dx from both sides. That would make this part go to 0, and this ends up over here. So I hope you can see the little bit of algebra I did here. Now here's the good news. It goes from being a mess to almost being done. If you look now, we have this term has a factor of dy dx. This term has a factor of dy dx. So we can factor that out. So here it is. I factor it out. Just to test if it worked, we can try it. Dy dx times 12y x squared plus y squared is in fact this piece again. So the dy dx would go back here and here. So if you can see now, what we have is we have this thing broken up. We have dy dx and we have this term, and we have this quantity right here. All we want is the dy dx, so we're going to divide both sides by this, and that's what I'm doing right here. Yeah? Divide both sides by that. Get down to dy dx. Dy dx is this. Look what I did here. It looks kind of weird, I think. See this negative 100x here? I just moved it here because what I'm going to do is, what I could do here is I could simplify. I chose not to. I know this problem was really challenging. Actually, if you graph this, it makes something called a lemniscate. It's actually pretty cool. I'm sorry, I know it was a lot of work. I hope you took your time on it and copied the notes that you needed. This is a really, really good example. It's kind of tricky, but it has a lot of cool stuff to it. And if you can do this, you can do most implicit differentiation. So hang in there. Good job.